for getting any questions out, that would be appreciated. So, so we've got aging, say we've got aging infrastructure out there, and what impacts that infrastructure? What causes us problems? What keeps us up at night? Well, we've got the pipes out there will often develop cracks and begin to leak. Our aging infrastructure could cause us problems with compliance. Are we meeting our regulatory requirements? If we have any sanitary sewer overflows, those are major things that's important because we'll cause problems potentially for lakes, rivers, public health, things of that nature. Do we have any restrictions in our collection system? Is there a broken pipe that's blocking the sewer? Is there the flow of the sewer? Is there a fatberg or something like that that's blocking it? And do we have corrosion out in our collection system that causes the pipes to deteriorate, potentially leak into the ground around them? And then ultimately, are we overloading our wastewater treatment plant or our pumping equipment because we're sending too much water, possibly due to inflow and infiltration in our system? So this is just, these photos kind of depict some of the different problems that we can see. Pipes can develop cracks. The joints may not be sealed properly. That corrosion I mentioned, and we could corrode from the inside out of the pipe. And that would allow, all these things would potentially allow water to get in or out of the system. We've got this figure here that shows some of the things that can happen with corrosion. What wastewater has different properties. There's biological processes that could go on if this material is allowed to stay in the mains. And we'll talk more about this as we go through this presentation. Here's actually a slide that covers hydrogen sulfide corrosion, and the slide it's not super important what we're talking about here. It's more or less the concept, the idea that things can happen out in our collection system. So we can have, if we have debris that settles out, it can create an anaerobic environment. Anaerobic bacteria can thrive there. And so we've got a slime layer and sludge layer, and you can see where that accumulates at the bottom of the pipe here. So then sulfur reducing bacteria in the pipe can produce hydrogen sulfide gas, and then sulfur oxidizing bacteria convert that hydrogen sulfide gas into sulfuric acid. Sulfuric acid is going to work on the pipes and cause corrosion. And we can, that corrosion can affect metal pipes, concrete pipes, and the cement joints of clay pipes. And we can also experience an increase in ammonia levels through this process. So it's just showing that, these things can cause our assets to deteriorate. So we've got a little diagram here that shows several of the different things that we might see out in our collection system. We've got a home, and we've got sanitary sewer. Okay. Oh, I'm using the pointer on the wrong monitor. Sorry. So we've got household wastewater, sanitary sewer, storm drain. We've got water from a ditch that gets potentially in the curb line. We've got catch basin, different waterways. So cross connections with the storm sewer and connections to roof gutters can lead to SSOs. So we're putting too much water in. Water's coming in from places that it shouldn't be coming, and it's causing us to have overflows. If we've got defects in the sewer mains, that can lead to infiltration of groundwater and seepage of wastewater. All these things are adding up. And then we can also see sanitary sewer overflows that contaminate water sources, lakes, rivers, streams of that nature, things of that nature. So, and then excess wet weather flows from infiltration can overload those wastewater treatment plants and lagoons. Just they weren't designed to handle the amount of water we might be sending to them. So what are our sources of I&I? We have two different things. I&I is made up of inflow and infiltration. And inflow, those are things that are, if we look at this diagram here, the things that are in blue are inflows. The things that are in brown are infiltration. So we've got roof drains, we've got foundation drains. You could have an uncapped clean out. Storm, if we have a cross connection between the storm sewer and the sanitary sewers, those things are all could be inflows. So the water is flowing in at points where it could be easily disconnected or separated. And infiltration is primarily from damage that we find to the pipes. Could be the manhole, could be the pipes, could be leads, sewer laterals, things of that nature. So sanitary sewer overflows. So with those, we know that the collection system, when they happen, we know that the infrastructure is not capable of handling the flows that come from excess I&I. So it's either that, or there could be a blockage, or if something failed, like a pump that allows that extra water to back up or get into the point where it overflows. It's not fully treated. And anytime, that's a compliance issue, because anytime you've got raw wastewater or partially treated wastewater that's entering the environment, it definitely would impact public or environmental health. We've got a short little video to show. As you can see, we've got this water's coming out of this manhole, and it's entering this little stream or ditch, river, whatever we have here. And so that's directly impacting that. Now that could go out go to a lake, and there could be a beach or something like in that nature, or it could go to where there's a drinking water intake of sorts. All right. So let's move on to our next slide. Another potential source of excess water could be sump pumps. They can discharge a great deal of water, and it's one of the largest contributors of inflow. So if we look here, it says a single sump pump can send more than 7,000 gallons of water to the system during a rainfall event, which is roughly the same amount as the average daily flow from 18 homes. So that's a lot. If we're adding 18 times the natural amount at one home, imagine if all 18 of those are doing that. So that's why if we've got issues with sump pumps that are connected to our sanitary sewer, it can cause a lot of problems out there. Our collection systems were not made to handle that water, and our treatment facilities also were not made to handle that water. Now, if this is going to a combined sewer, that could be a different story. But ideally, we're separating all of our sanitary and non-contaminated water before that happens. We just show some of the different components here of a sump system for those who may not be familiar. So we've got a foundation drain tile that's going to bring the water in. We've got a little sump here to collect the water, and we've got a pump in here, and that pumps it out. And ideally, this goes out either to a storm sewer or out on the ground, or potentially underground if it's feasible for the location, but it shouldn't go to the sanitary sewer. So we talked about adding too much water to a wastewater treatment plant. or a lagoon. So we can see here that, the example on the top left, we have inflow. We've got water that's entering a manhole cover that maybe isn't sealed properly, has openings in it, is in a depression or a low area in the street potentially, or someplace else. We've also got infiltration from those cracks in the pipe, and then that's going out to the lagoon. And when we put that much extra water to the lagoon, we end up overloading it, and quite often results in emergency discharges. And that can cause us some compliance issues. We see the figure on the top right. It looks like there's just a whole lot of water coming through. And when that happens, we end up having to use more electricity. Our costs go up. The potential for that plant to be overloaded occurs, as and some of the other impacts to a wastewater treatment plant can be that we're washing out our microorganisms. The rate that the water is traveling through the treatment plant is too high. Our detention times, if we need a certain amount of time for something to happen within our wastewater treatment plant, we're going to have to reduce those times because of how much water we're having to treat. And so maybe we're not meeting those requirements. As I had said, you might have to have, if you have a lagoon, you might have to have an emergency discharge. And so we can have a lot of issues that result from these, from infiltration and inflow into a sewer system. So here we've got a figure to the left. They mentioned fatbergs. I mentioned it earlier. That's a combination of a bunch of different things typically. The fats, oils, greases, along with, in this case, wipes. Wipes have become the bane, I think, of the wastewater world. And so all these things add up. I did a little searching, and I found that the largest recorded fatberg was nicknamed Fatty McFatberg, and it was found in London in 2017. It weighed 130 tons and was 820 feet long. And obviously, that didn't just happen overnight. That was something that had happened, and there was probably some flow that could get past the fatberg, but yeah, this is a big problem. We can see it, in actual photos. We've got roots on the bottom left. We've got the majority of the pipe, both of these pipes are blocked. And then on the right, this is from the city of Tallahassee, and it mentions the, frog will clog. It's a way to get the information out to the public. And they actually have a system here, it appears, to collect used cooking oil. So that's a good thing. Use it for biofuels to power city trucks and vehicles. So that's a good way to turn a bad situation into a good, I guess, and take that out of the system and make use of it. So it's important in our distribution systems that we have, in our collection systems, that we have a minimum flow velocity, and that's to avoid those that stuff from backing up. The solids settling out in the pipes. So if we can have a minimum flow velocity of around 2.5 feet per second, it's going to hopefully keep any obstructions and any defects. It's going to allow that flow to carry through the pipe and to not build up. But if we don't, then we have those solids that settle out in the pipes, and which we also have increased ammonia formation. We have sepsicity and hydrogen sulfide corrosion. And sepsicity is a condition of wastewater where it becomes stagnant. I mentioned it a little before. Oxygen deprived. It's anaerobic. It's foul smelling. It's characterized by the breakdown of organic matter by bacteria, and it produces that hydrogen sulfide gas. It smells like rotten eggs, and it corrodes the pipes. So we want to avoid that. The increased odors can be a result of not having enough flow. And then we can also get blockages and stop the flow of the water in the pipe. So what are we going to be talking about today? So we'll be discussing several things here. We'll look at an overview of asset management principles and components. We'll look at the causes of failures in our assets in our collection system. We'll look at some condition assessment strategies for our wastewater assets, and what essential questions are we going to look at? So we need to look at what types of things can happen to assets that leads to the need for replacement, rehab, and repair. So what things can happen to our assets? What are the ways we can analyze the current state of our assets? So we want to know where they're at now so that we can figure out, help figure out an order that we need to do that replacement, rehab, or repair. And how can we predict and prevent failure of those assets? So we'd rather address them before they fail in most cases. All right. So what does asset management do? So it's going to allow the utility to do several things. So we're going to be able to look forward and plan and prioritize for our future maintenance, repair, and replacement activities. So we want to know what we need to do out into the future to make sure that our system is operating properly. We're going to diagnose what actions are needed to improve the asset performance, what can be done to make it work better. And then ultimately, we're going to create a financial plan that's going to allow us to maintain our system, to do all the things we need to do, extend the life of these assets, and hopefully save money as we do that. Why do we do asset management? So asset management is a long-term planning process to make sure that we do it's a long-term process. Planned maintenance, we got to do our planned maintenance. We need to ensure that our assets are repaired and replaced on time, not before they fail. And we want to make sure that there's enough money to handle those different items. And asset management is a continual practice. It's not a one-time we do it, put it on a shelf and forget about it, because it can help minimize our life cycle costs and make sure that we deliver desired service levels. And service levels is one of the harder things, I think, in my mind, to come up with. But it's easy to put numbers to things, but we'll talk a little bit about service levels and why that is. So asset management has 5 components. So there's the asset inventory, that's our data collection. So we're going to put together all the information that we have about all our assets right now. That can be as big or as small as you want it to be. We're going to look at the critical assets. So what's the importance of each one of these assets we're going to see it. We're going to analyze that. We're going to mitigate any of the risks that might come along with those. And we're going to look at the asset life cycle. How long what's the useful life or something, and when does it need to be replaced? And then the levels of service, we're going to talk about that. And that's setting the minimum service requirement for each one of the assets. What does that asset need to do for us as a minimum? And then the long-term financial planning. So that's going to could be a capital improvement plan, but we need to establish those funds and for rehab and replacement, so that when the time comes, we have the money available to do that project. All right, so we'll go more in depth into asset inventory. So asset inventory, we collect data to determine the current state of assets. So there's a whole bunch of different things that we can look at with that. We want to look at the condition. We may need to know the location, the type. It could be a manufacturer. We collect a lot of information. And the important thing is that we get at least a minimal amount. I hate to see that people don't start because they don't have all the information. So you need to get some, but you can't let it hold you up from working forward through the process. And then establish a framework to collect additional / future asset data. As we do this, if we replace something, then that's going to come off of our inventory, but chances are we're adding something on. So we need to make sure that we have in place the ability to add and subtract from our asset inventory. And this will all help us make decisions about what we're doing with our infrastructure in the future. Where do we get our information from? So there's a lot of different places we can get information from. As-built plans, that's a great source. So, when something was built, the engineer came along and, they had the original plans, but this is how it was actually built. They put those, they give the community those plans. Those are one of the best sources of what's actually out there and how it was constructed. You can have collection system maps, that show where things are. Could be how many manholes are there, where they're located, things of that nature. Records. So whether you do your own repairs or you've got contractors that do repairs, those records can be really important because they'll speak to, do you have a problem area in your collection system? We're constantly having breaks in our sewer mains in this area or that. And that information is very helpful when we're collecting, when we collect information about all these assets. Operator knowledge and experience. Some of the most important things out there are our operators, and they know because they deal with this on a daily basis. And then equipment manuals. What do we know about these things? Let's look at those manuals. We bought a piece of equipment, a manual came with it, and typically it just sits on the shelf until we have a problem, but there could be valuable information about that asset that's included in that manual. And then finally, inspections. So inspections are going to help us to know what's the current condition of an asset is, and also, where is it trending? Is that asset deteriorating? Is it seem to be doing fine? What's how's that asset we're operating for us? And so that inventory is a framework, and we'll collect and analyze the data. We'll use that to make future plans. So we've got for instances here, we've got a manhole. It's concrete. It's 40 years old. It's in good condition. Everything sounds good with that. Over here, we've got a lift station. It's 20 years old. There's two 10 horsepower submersible pumps. It's undersized for the increased flows that it's experiencing. So that would cause me to think, okay, so what happened? Why are the flows increasing? Do we have infiltration and inflow? Has it just been an issue that's associated with growth? Has the community grown, and that's why all of a sudden it's undersized? These are things that hopefully come out, thoughts that come from looking at these different things. And then in this case, we've got at the treatment plant headworks, we've got screening, grit removal, we've got some submersible lift pumps, and in that case, the screens and the grit separator are failing. What could happen if those aren't fixed? These are all things that collecting this data will help. These are thoughts that we need to have after we've collected this information. And so the asset condition rating, so you see that it goes from condition rating of a 5, which is the asset is unserviceable. So that means it's there's no sense in, or maybe there's no sense in, or maybe it's not. We can't repair that asset. So that's saying in this In this instance, that means over 50% of the asset requirement requires replacement. And that goes down to a 1, which is considered, that assets in new or excellent condition. You only need to do normal routine maintenance on that. And then the numbers are in between there as well. So it's when we look at this, we want to figure out where does our asset fit into this? And there's no exact science to this. Quite often what ends up happening is I think that communities look at this as they compare it to their other assets. So asset condition data provides information about what needs to be done to improve or maintain assets. We've got an example here of a test of a 20-year-old submersible pump in a wastewater lift station indicates that it has lost 10% efficiency. Rating is a 3. So if we look at that rating of 3, it's a moderate deterioration, significant maintenance required, 10 to 20% of its life or efficiency. Next steps would include checking the impeller clearance, the bearing condition, and electrical testing to evaluate whether the pump should be maintained, repaired, run as is, or replaced. So that's asset condition rating. What do we need to look at when we do these condition ratings? How much remaining useful life is there? That's important because if there's no useful life, then that condition that has effect on our condition. How is it meeting our service level? How is it compared to what it's supposed to do? If it's supposed to pump 100 gallons a minute and it's only pumping 50 gallons a minute, then it's not meeting that. How reliable is it? Can we count on it, or does it work some of the time? And then what's the history? Has this been a problem for us for years, or is there something recently that happened with this? Does this cause us to not meet any of our regulatory requirements? Are we meeting compliance? And then how easy is it to maintain that? Sometimes that's a big factor because it's just too difficult to maintain. And here we have an example of an asset spreadsheet. So when you gather all this information, these are some of the things that you might gather, and you put them into a spreadsheet. It's helpful because then you make sure you have all the information, and you can do a little comparison as you look at them. Excuse me. So if we look at this collection main 1, it's 384 feet of 12-inch clay pipe with a condition rating of 4, which means it's poor. It's expected to be replaced in 10 years at a cost of $30,720. And we're going to take that $30,720 and we're gonna put. We know that it's going to take 10 years, so every year we're going to put in 1/10 of that cost into our reserve fund, so that when that 10 years has gone by, we'll have the money to replace that. Next, if we look at collection main 3, it's got a condition rating of 5, which means very poor, and 1 year before it needs to be replaced. And the cost for that is $42,900. So that is the highest risk or criticality of all of our assets that we have, that 5, and it's also the highest as far as our need to be replaced. So the other thing with that is that we only have 1 year to get that $42,900 saved up. And you could add additional information. There's other stuff that you could have in this. You could have results of your inspection findings. You could have links to manuals. You could have the model and serial numbers. Who's the vendor that you bought the piece of equipment from. There's all sorts of things that you can have in there. But like I said before, I make sure that if you're doing one of these, you don't get held up waiting on all that information, because you may not have it for every one of your assets. And the important thing is to make sure that you move this process along. So if you'd like to, you can share in the chat any ways that this information would you think might be useful to you. We'll give a couple moments in case anybody wants to put. So Dennis says for planning maintenance, definitely. Yeah, completing your asset management plans. Yes, it's important. We need to have that. We need to gather all this information together. Future capital improvement projects. Yes. Yep. I think you guys are budgets and rates. That's all comes together. 1, 5, 10-year budget planning, ordering spare parts. Yeah, Greg. Convincing boards to approve upgrades and purchases. Oh yeah, that's always a challenge. And quite often, the more information you have when it comes to trying to get things past boards, the better. I mean, it's helpful to have things that are obviously not personal preferences. You can actually put some sort of justification behind them. All right. Well, thank you all for participating in that. And so now we're going to look at our second of the 5 components of asset management, critical assets. So we need to analyze the level of risk associated with potential failure. So what can happen if that asset fails? Is it a big deal? Is it a little deal? That's going to be important when to determining which of our assets we prioritize for replacement. And then prioritize the use of resources, how we're going to spend our money. We need, or our time. It's important to know. And typically we work on the more critical things. And then identify any mitigation efforts that might be necessary. So if we look at these 2 figures here, on the left is a clay pipe that's relatively new, but as you can see, there's all sorts of cracks, potential separations. So that pipe is actually not in the greatest of shape. The pipe on the right looks to be very old. That's a brick pipe. I don't know how long it may have been in service for 100 years, but it looks pretty clean and pretty good shape. So, which collection pipe has a higher priority for repair or replacement? Had somebody not looked at these pipes, you might think that the pipe on the right was the higher priority, but it doesn't appear that from these photos. Criticality analysis. What's criticality determined by? We need to look at what are the chances that this asset could fail? What's the probability of failure? So POF is going to be something that we'll talk about. And then what's the consequence? What's the result of that failure? So, what are the chances? And then what would happen if it fails? And so we'll use these 2 different things in a rating system. We'll give them a numerical value for each of our assets. We'll give them a probability of failure number. We'll give them a consequence of failure number. And that's all going to be taken into consideration to come up with our overall criticality score. And so it's a tool that we can use to make comparisons. And so if we do this, we're going to take our probability of failure, multiply that by our consequence of failure, and that'll give us our criticality. So we're going to be able to put numbers. Initially, we put numbers to the POF and numbers to the COF, and then ultimately to our criticality. So the probability of failure, we want to look at that. This is, there's a scale for this with the performance ratings from unlikely or improbable. We give that a low rating or a 1 up to imminent. Something is going to happen, at some point in the future. We know that that's going to fail. It could be a situation where we know it's going to fail at any time, and that's going to require an immediate. So if it's improbable, it's going to have a low number. If it's imminent, it's going to have a high number. And then we have, we have other factors in between. Remote. So there's a remote chance. It's possible, it's probable, and on to imminent as we go down there. We're going to base condition assessment combined with root causes and environmental factors present in operating conditions. So there's, and then the condition is not always the same as the probability. All right, you will look at the two different scenarios to get that point. So in scenario 1, we've got a condition, the condition of we have a 20-year-old submersible pump that has some minor external corrosion, and it's lost 3% of its efficiency. In this case, we're rating this condition as a 3, so it's got moderate deterioration. And what are the environmental factors? What's going on with this? So the pump operates 8 hours a day within the optimal range of its pump curve. The water is not corrosive or scale forming. So that pump is pretty stable. And then if we look at scenario 2, we've got a brand new submersible. So it's in good condition. It's got stainless steel components. And we've rated that as excellent condition. I mean, it's brand new. Why wouldn't it be? But what are the environmental factors with that pump? The pump operates at the extreme limits of its pump curve and continually at its maximum head. It operates 24 hours a day, and it cavitates the entire time it pumps highly corrosive water. So that pump it's in good condition. Well, let's see. Well, which pump is most likely to fail? So in scenario 2, that pump's in good condition, but it's operating in a very difficult situation. Whereas pump in scenario 1, that submersible pump, it's kind of working right in its sweet spot. So we'd expect that one to work for a long time. So the condition of the first pump is worse than the condition of the second pump, but the second pump, I think, we can all agree, is more likely to fail just because of that environment that it's operating in. So the consequence of failure depends on the degree and severity of the disruption. So if we want to know what's going to happen as a result of the failure, we need to know, how severe it is, how much that's going to affect us. So once again, if it's insignificant, in this case, it's going to get a rating of 1, and that goes up to catastrophic with a rating of 5. So these numbers are setting themselves up so that the better it is, the lower the rating, and we'll see as we go on farther how that affects. But our consequence of failure could be insignificant at a 1, it could be minor at a 2, move up to moderate at a 3, and major at a 4, with catastrophic meaning that maybe the entire system is out. A moderate disruption might take out, a certain percentage of our system, but catastrophic is going to take out the entire system. So more on consequence of failure. So we're trying to put numbers to the degree of disruption or the impact that it's going to have on our community, our utility, the people who receive our services. And what kind of things do we need to look at? How long is that outage going to be? How long is the customer is going to be without service? Are we going to cause any other damage by having those people out of service, or by what it takes to fix the situation? Are we going to meet our regulatory requirements? Are we going to end up with violations because this was out and it wasn't operating? And then what's the cost to fix the problem? Are we affecting any public safety or health? If we look at this diagram, we've got barriers right along this open hole. I mean, if somebody had driven through there, operators there or repair people working on this, I mean, they could be affected, or if this is out, does that cause people to not be able to flush their toilets, to not be able to live the way they should be? And then is this causing it to back up or overflow into lakes, rivers, streams, things like that? So let's look at a criticality example. So if we want to we'll take an example. We've got a section of collection trunk main that's likely to fail within the next 5 years unless we fix it, unless we repair, rehab, or replace it. If the main were to fail, it would impact 1/4 of the city collection system. Okay, sounds like quite a bit to me. So we're going to give that a probability of failure because we know it's going to fail within the next 5 years. It's probable. We're going to give that a factor of 4. And then what's the consequence of failure? We're going to give that also a 4, because that would be considered a major disruption. It's not the entire system, but it's a good portion of it. And we could result in some sanitary sewer overflows. So if we're going to take and determine our criticality, we need to take that potential of failure and times the consequence, and we multiply those two together. They're both 4. That gives us a criticality of 16. So how do we look at that if we're going to, compare that to other things? So as I said, the higher the criticality, that means there's a greater, we have to worry about those higher criticalities more than the lowers. And that's where we need to focus our efforts and our finances towards those high criticality assets. Highest risk of failure are assets with criticality scores of 16 or greater. So if we're up in this top right quadrant, those are our problem children, and those would be the ones that we should address first. And then if at all possible, we want to make sure that we're doing the PM, the preventive maintenance, to avoid any of those problems. And throughout this process, we're going to end up developing that funding so that we can repair or replace, fix those assets. We need to set aside that money. So as you can see, we've got a POF of 4, a COF of 4, and gives us a criticality of 16. We can just we use those numbers in the chart, and that's where we're at. And so I had said that, if we're working in that upper right quadrant, that's where we need to address something pretty quick. We need to come up with a solution for the things that are both high consequence of failure and high likelihood or probability of failure. And then the areas, in blue, those quadrants, we need to make sure that we're doing the monitoring so we can be aware of how it's operating, and then any targeted maintenance that might help extend, either reduce the consequence or the likelihood of those failures. And if we're in the bottom left, it's pretty much just routine monitoring. We're checking on it regularly, but and then doing the PM, but it's not likely that it's going to fail. So those are the areas that we can maybe take a little breather on. So now we're to our first poll. Pole 1, 2 wastewater mains are assessed. Main number 1 has a probability of failure of a 4 and a consequence of failure of 3. Main number 2 has a probability of failure of 3 and a consequence of failure of 5. Which has the highest priority based on criticality? Main 1, main 2, or you don't have enough information to make that determination?
I'd just like to offer a reminder that if you can't see the poll, you might have pop-up blocker issues with your Zoom window, and it's totally fine to put your answer right into the chat window if that is an issue for you.
All right. Here it's 73%. People 75. All right. We got some answers in the chat as well. All right. I'm going to end the poll and we will talk about this. I'll share the results with everybody. So 88% of the people said main 2. We had 7% that said not enough information. And then we had 5% that said main 1. It looks like people in the chat put B as well, or main 2. All right. So let's go on and we will look at this. All right, so our solution is we're going to use that criticality matrix, and we're going to put in our probability of failures, and then we're going to put in our consequence of failures. So in main 1, we've got 4 and 3. So if we take our 4 and our 3, so that means that we're going to have a 12 when that's said and done. And then we look at main 2, we've got 3 and we've got 5. So that gives us 15, which would tell us that based off that criticality scores, our highest priority is going to be main number 2. All right. Could we use more information? Sure. It's always good to know more about what's going on. One of the things that comes to mind to me is that when I was dealing with this kind of stuff, quite often we would look at things that other factors. If you had this situation and say the road was going to be rebuilt over main 1 next year, then maybe that changes your scoring, and you decide that main 1 has to be done before main 2, because the last thing you want to do is dig up a new road to replace a main underneath it. So there's other factors that come into place, but in this simplified version, that's what I think you need to make your decisions. So the third of our 5 components is asset life cycle. So we want to operate those assets so that they perform well enough or as expected throughout their entire useful life. We want to plan their replacement of the assets based off their remaining useful life, and we want to apply the correct type of maintenance and operation to minimize the cost of that asset over its life cycle. All right, so what is the life cycle of an asset? It begins when the asset's installed, and it ends when we take that out of commission. Why would we take it out of commission? Because its performance falls below the minimum acceptable levels, or it can't be restored. So we've got the asset acquisition. That's the initial investment and the date that we purchase the asset or the asset's placed into service. We've got the operation of the asset. Those are the costs and related tasks throughout the useful life of the asset. We've got the maintenance. So those are the costs to perform the maintenance and any repairs that are made on the asset during its life cycle. And finally, we've got the disposal. That's when we're going to decommission, remove, replace, and the costs associated with doing that. So we talked about the remaining life of assets. So that's important in this process because if an asset doesn't have any life left, then there's the need for the desire to put maintenance into it becomes less and less. We use that for creating our estimates. With underground assets, it can be a little difficult because quite often, we don't see those assets, and the information that we have may not be that accurate because we just don't know how good a shape something is when it's buried underground. But we can find that information out if we do some inspection. And it's important to gather whatever inspection data that you can whenever it's possible. And there's a lot of different ways. Greg will talk about quite a few different ways to do that later in this presentation. So the expected asset life is we take that number and then we subtract off our current age, and that'll give us an idea of what the remaining age is. But quite often we'll find that maybe something is going to live, beyond its asset life, and we may have to modify that based off of information that we come across as we go through. So activities over the life of an asset. What are the events that might occur over the life of in this case, a steel 500,000 gallon aeration basin? So what asset management events might we expect? All right, so we've got an expected useful life for that asset of 50 years, assuming that we do, adequate maintenance on it. So this table shows us a list of the different activities that we might take on that basin. It gives us a frequency, how often we might have to do that activity, and then it gives us an annualized cost. So on a daily basis, we're going to do different things. We're not really going to put a cost to that because those things are pretty routine typically. But if we look at some of the other things that we might do, so if we were going to recoat interior surfaces and do some repairs, maybe we're doing that every 10 years and it costs $25,000 to do. We might repair some valves and piping if that costs $2,500. And once again, we're doing it every 10 years. As we can see, we look down this chart, there's different activities and they have different costs. And maybe these aren't right on, but it's just for an example. But we can take and look at if we're taking these things and they cost, we're doing a certain amount over a certain number of years, we can take and figure out what it's cost on an annual basis. And so if it's a $25,000 cost every 10 years, that means that on average, it's going to cost $2,500 each year. And if we were putting aside money, we'd want to put aside $2,500 each year. So we go through all these different things that might be required. And in a 50-year life cycle, it could cost us, our original purchase prices for this was $1,250,000, but it's going to last us 50 years. So that means that on an annual basis, the depreciation of that $1.25 million over the 50 years is going to be $25,000 a year. So if we take and we combine all of these things, and that's going to if we all of our annualized costs are going to amount to $29,450 per year over 50 years. All right. So now in comparison, so we're gonna take that same 500,000 gallon aeration basin, and we're not gonna do any maintenance on it. We're just gonna we're gonna we're gonna run it until it fails. So if we're gonna do that, it's not likely that it's going to last 50 years. It's probably going to drop down to a 20-year expected useful life on that. The other thing that we're going to see is because we're not doing routine maintenance on it, our treatment efficiency, it's not going to work as well because we're not doing things just to keep it up. We're just going to let it fail. And then, there's a potential that things, aren't as safe because we're not doing the maintenance. We don't see the things that could cause safety issues for our operators. But what we're going to see is that the annualized asset cost increases. So if we take this same table, all these different activities, we're not doing them, but we don't have any cost associated with those because we're not doing them. But the thing that we do have is we still have that $1.25 million price tag. And since it's only going to last 20 years, it's going to cost us $62,500 per year. So as you remember, I mean, it's not going to work as well. It could potentially cause some safety factors. And it's not going to work, and it's only going to last 20 years. So if we do those, we summarize all our annual costs like we did in the table before, and they were $29,450 a year if we did that maintenance. Now it's going to cost us $62,500 per year. And so there's an example of how we can look at a life cycle cost and the importance of maintenance and minimizing that life cycle cost. So we've got a discussion here. Think about the most expensive asset in your utility. Which of the following do you think will occur for this asset in the next 10 years? Continued routine or predictive maintenance only. B, a planned major repair or rehab activity. C, an unexpected breakdown. Or D, you're going to have to replace that asset. All right, the poll is up. We're getting responses. We'll give a few more seconds. We're up to about 73% of the people who have responded. All right, any last minutes? Okay, I'm going to end the poll and share the results. So as you can see, we had 38% of the people said planned major repair or rehab activity, 28% continued routine or predictive maintenance only. And then it looks like it's 19% for C and an unexpected breakdown, and then 15% D, asset replacement. And the right answer is whatever answer is right for you. Because this is based off of what you think. All right, well, thank you for participating in that. We'll be taking a couple more slides and then we'll take a 10-minute break here. So the fourth of the 5 components of asset management is levels of service. So levels of service, to me, is one of the harder ones to come up with. But so it's we're going to compare our current asset performance to required performance. So that could be an internal service. It could be a customer service here. It could be a regulatory service level. And we'll compare the different asset replacement options. And then, as I said, it will establish utility and customer service level. So who's the customer? Is that the regulatory agency? Is that your residents? Electrical measurements for pump motors can provide information about performance and remaining life, which can help plan for things. So we've got a level of service example. We've got a wastewater lift station that needs to be able to deliver a minimum flow of 150 gallons per minute at a pressure of 40 PSI in order to move wastewater efficiently from the wet well and through the force main. So here's some examples of factors that could cause the level of service to fall below the minimum. So we could have pump bearing fails. We could have some electrical imbalances. The insulation on the pump motor could deteriorate. The impeller could be damaged or it needs to be adjusted. Or force main or the check valve becomes clogged. How could each factor affect the level of service delivered by the lift station? What types of repairs or tests would be appropriate to assess these factors? So if you wouldn't mind sharing that information in the chat, and we will take a 10-minute break. Lori maybe can set a timer for us, and we'll come back and discuss those things.
Okay, so I did set a break timer. If you look at the top of your Zoom window and kind of hover over up there, you should be able to see the countdown timer. We're going to go ahead and take that 10-minute break, and I hope everybody has a good one. We'll see you back on the other side.
Here, so just so we know what type of repairs or tests would be appropriate to assess the different factors that are here. So we'll go on, and I'm going to look at talk about the last of our 5 components, and that would be the long-term financial planning. That's probably why one of the more important reasons is why we're going through this whole process, is so that we have an idea of what it might cost for replacement, maintenance, or repair in the future. We can plan for it. This will help us create a capital improvement plan, and we'll be able to put the costs of that infrastructure into our budget to make sure that we have the money. Yeah, we need to know when those assets will require replacement and how much it will cost. So here we've got an example of financial planning. We've got these different projects, collection mains, a couple of those. We've replacement, a lining. We've got rehab of a lift station. We've got a manual repair. And then in the next column, it says how many years until the project must begin. So then that gives us an idea how long we have to set that money aside. And then finally, we have the cost of each one of those. And then the reserve that's required each year is the cost divided by the number of years that we have to put those to save that money or set that money aside. So that says that so our total capital improvement reserve required in the current year is $48,717 based off of those costs and the number of years that we have to pay. Prioritized projects are planned with a start date and estimated cost spread over the planning time window. So that's the idea where we're taking these the cost and we're dividing that by the number of years to the project. Reserves are earmarked toward each project. Annual contributions to reserves become part of the utility budget. So we have to make sure that we put that stuff in our budget. Smaller projects and repairs can be absorbed by the operations budget. So quite often what you'll have is there's a minimum threshold that a dollar amount that we consider for these. If it's less than that, then we put that into our operations budget. And so if it's a $50 concrete ring to raise a manhole, you're not going to have, put that into that capital improvement plan budget because it's not significant enough. I mean, if you had to do one and it, for instance, it was 10 years out, you're going to save $5 a year to make that happen. So it's just kind of using a little bit of common sense in that regard. All right, so next we're going to talk about asset performance and some failure modes. So there's several different things that can cause an asset to fail. You could have mechanical failures. You've got a big part of that asset breaks or fails. You could have human error. It was put together wrong. It wasn't operated correctly. Overload. You used it beyond what it was designed to be used for, or at what amount it was designed to be used for. Corrosion. We talked about corrosion of the sewer pipes. That component becomes deteriorated through chemicals. Erosion. It's just the asset becomes worn away. Fatigue is when it weakens over time and ends up breaking through that. And there's a lot of different things that can influence asset failure. For mechanical stuff, we could have the lack of lubrication. It could be pH, can affect a lot of different components or assets. How it was designed, electrical issues, how much we use it. There's several different things. So asset failure modes, there's a lot of different things that can lead to the condition where an asset is no longer able to serve its purpose, or it's reached the end of its useful life. The physical mortality due to weight or to wear, fatigue, corrosion, the asset's no longer efficient to operate. Those can both be chalked up to asset deterioration. And then the next two issues, if we've got new requirements that exceed our design capacity, or no longer meet the service levels as it was designed, those are external factors. So those are things that come about. That asset was fine when it was installed, but things have changed, and what we need out of it isn't the same as when it was installed. So our assets are going to fall into one of these different failure modes. So let's look at an asset condition, a performance curve here. So if we look at this, we've got our performance curve here in red. For instance, here's our current condition. That's where we're at now in our timeline. And at this, the performance is higher and it's going to deteriorate. It's going to go down through time. The the difference between our current condition and this threshold where that's as low as it can go. That's the remaining service life. And then above this threshold is the asset is serviceable, and below the asset is no longer serviceable. And so we're gonna make decisions on what we do with that asset, whether we replace it or not, based off of how it performs. And eventually it's going to fall below that threshold. Does condition only go in one direction? Typically it only goes down. As I said, the threshold value, that's the point at which the asset can no longer deliver the necessary service level. At that point, we're going to have to do something about it. And this is probably a little bit more realistic. This is a decay curve when we're looking at asset condition. And so with this, our performance is decreasing. At a certain point, it decreases at a higher rate here along this curve. So we're going along through time, and it's operating pretty good. And then all of a sudden, it's going to just start to drop off. And we've got different levels. We've got excellent, good, fair, and poor performance levels. And you'd expect that you're going to see more breakdowns as time goes on and that curve drops. And that should be, having those breakdowns should alert you that you're going to need to do something about it. So this follows that asset or so that decay curve. So we look at the asset health here, this figure at the bottom. There's a point where the failure starts to occur. And then these are some of the things that maybe if we're doing these things, we'd be able to tell that it's starting to fail. So we look at these different points on these curves. So if we want to predict motor and bearing failures, these different inspection methods are going to detect those before they occur. So, different ultrasound is likely to detect it earlier than an oil analysis, which is earlier than vibration, or infrared thermography. And finally, an audio or audible or visual inspection is going to be one of the last things. By that time, it's probably it's getting to the point where it's too late, because that failure is well underway, and we're not able to see or to hear that, as well as some of these other inspection methods. And then in this, it's the importance of this is to show that we can't have a lag between when it starts into failure mode and when we discover it. And the longer it takes, the more that it's more expensive that it's going to be for us to correct that issue. The cost keeps going up. If this time between when it fails and we figure it out is too much, we're going to have the cost increases. And sometimes, it's just too late. So let's take an example. A bearing fails in a pump motor. By the time it becomes obvious because of vibration and noise, the casing and wiring are already damaged due to overheating. Therefore, the entire pump needs to be replaced instead of just the bearing. So with this, the idea is that we're trying to close that gap up between the time that it starts, that failure is starting, and when we discover that it is, and hopefully we can do that. We can save on the cost. For critical asset failure modes, sensors and inspection methods can be implemented for earlier detection and repair before damages occur. So let's look at a lift station pump motor. The bearings are periodically assessed with ultrasound, vibration analysis, or infrared heat detection, and can be replaced before they begin to fail, preventing the additional damage to the pump and motor. A motor protection relay can be integrated to create an alarm when there is overheating or an overamperage current draw. So these are just two examples of how failure mode analysis can be used to help mitigate potential failures for a multiple component asset. What else could we do? All right, so let's look at this example of a lift station system. There's several different components. We've got an electrical service to the panel. We've got level float switches. We've got a control panel. It's got relays, pump starters, alarms, level control sensors. We've got a pump motor. We've got a pump. It's got impellers, bearings, casings. We've got force main piping. So we're going to pump this to a force main. And we've got a check valve in the force main. All right, so what things do we have to think about? What are the critical points in the system that could cause the entire system to fail? So if we're gonna look at this lift station system, we gotta look at what are the critical points that could have the entire thing failing. And we also have to look at how do you prevent those assets from failing, and what can you do to detect any problems early on in this process. So failure mode effect analysis is it's a method for identifying potential ways a product, process, or system could fail, analyzing the impact of those failures, and prioritizing actions to prevent them, improving reliability, safety, and quality before the problems exist. So this concept is quite often used in engineering, manufacturing, healthcare. My understanding is that it originated with the US military in the 40s and 50s, and it was used by NASA for the Apollo missions. So I also believe that at some point or another, Ford Motors used this failure mode effect analysis. And so failure, with that, we're trying to look at what types of failures could occur. So we're looking at this before it actually happens. And then we're going to look at, what different assets can fail. That's the mode. The effect is what effect each type of failure has on this. And then we need to analyze the risk levels and any strategies that we can have to fix or avoid the situation. So in the example of a lift station, here we have, the electrical service. We've got electrical panel, floats or sensors, motor, force main, check valve. What are the different types of failures? We can look at those, and also the effects of each of these. And so, what are the types of motor failure that can result in damages or outages? In this case, overheating, bearing failure, amperage imbalances, and they can result in motor damage or outage. Now that we know we could cause a motor failure, we can design inspection and monitoring strategies for early detection. Now, this is another way to look at some of these failures. The root cause analysis is a systematic problem-solving method to find the fundamental reasons for issues, not just the symptoms, to prevent reoccurrence of those things. So in a root cause analysis, we have an event, which could be a breakdown, an outage, or something else. In this instance, we're going to say that that event is a lift station pump fails and it causes a sanitary sewer overflow. So next thing we're going to do, we're going to collect information. We're going to investigate the problem. We'll do that. The operator is going to pull the pump. They're going to check the motor, the pump, the power and control systems. We're going to analyze it. We're going to investigate what was the cause of the failure. Here, in this case, a voltage imbalance led to motor overheating. And the root cause was initiation of other nearby equipment on same circuit. So we had other equipment that was operating on that same circuit, and it caused a voltage imbalance. And what were contributing factors? In this case, the failing motor bearing. So now we come on to what are our solutions? All right. So we're going to use, to solve this, we're going to use a dedicated power source to operate the lift pump. We're going to routinely check and correct amperage and voltage imbalances. We're going to monitor the bearing, whether it's using ultrasound vibration analysis or infrared heat sensing, or a combination of those. And then we're on to our poll 3. Which of the following lift station situations best exemplifies an asset performance decay curve? Is it A, pumps in a lift station are getting clogged due to a malfunctioning upstream grease trap? B, a lift station has an increase in maintenance calls due to a developing motor problem? C, a lift station is having more SSOs this year due to heavy rain and illegal roof drains? Or D, all of the above? Okay, we're at about 75% of the people have responded. I will end the poll and share the results with everybody. So it appears that 64% of the people said that it was B, a lift station has an increase in maintenance calls due to a developing motor problem. We've got 35% said D, all of the above, and 1% said C, a lift station is having more SSOs this year due to heavy rain and illegal roof drains. So we'll move on, and the answer is B, a lift station has an increase in maintenance calls due to a developing motor problem. And the reason that that A and C would not be part of an asset performance decay curve is that both of those are things that are not truly associated with the performance of the of that lift station. Pumps in a lift station getting clogged due to a malfunctioning upstream grease trap is really, that's the problem with the grease trap. And then if you're having more SSOs due to heavy rain and illegal roof drains, that's really not indicative of the performance of the pump as it was designed. So Greg will be taking over now. All right, go through this process.
While you're doing that, I'm just going to make mention that there's a resource handout that I'm going to be dropping into the chat here for everyone. Again, there'll be a link and there'll be a PDF. They're both the same file.
Thank you, Daryl. Is my audio coming through okay?
Yeah, I can hear you.
Would you like to stay kind kind of just hang for a little bit longer. There's a couple questions in the queue, and before they get old, I'd like to have you give your perspective on them. And there was a question from or kind of a question comment from Jennifer earlier. A lot of great comments in here.
I
Uh,
have those on the Q&A list, so whenever you guys want to go through those.
yeah, that's can you could you read that question from Jennifer, please, Lori?
Yep, hang on here just a second. Okay, so we have just a handful on the list for Q&A. We had a comment from Daniel just about water-powered sump pumps are even worse on inflows, and just wanted you to know that that was a comment that was shared. And then
Yeah,
from,
that's that is true because they use a lot more water because it's a jet pump. It pushes water through to pull the water out of the sump. So yeah, that contributes orders of magnitude additional water. Um, so yes, definitely. Go ahead,
okay,
Larry.
yep, thanks. From Jennifer, she had a question, and this was when we were looking at the asset spreadsheet example. She was asking, is there an opportunity for cross-asset optimization, which would be including roads, water, and wastewater assets that typically reside within the same corridor?
Yeah, as I had said that, that was an example I think I used that those there's things outside of that actual asset itself that quite often dictate the need to replace an asset. And and so yeah, I don't know if it needs to be put into that table um, or not, but I think it definitely needs to be taken into consideration. You definitely, as I said, you don't want to have to dig up a recently paved road in order to repair something. If you can get it repaired while the road before the road gets repaved, that's probably the best.
Okay, thank you on that. I have a question from Daniel. The chart used for the tank was using initial construction cost, not replacement. Will there be any discussion about those differences for budgeting replacements?
Um, the estimate of cost is going to have to be, of course, the future cost. And one of the things that we do when we're helping a community to try to develop an asset management plan is we'll look at other similar projects that are going on in the area, and they still range quite a bit. The trying to use inflation, I've seen spreadsheets that try to use like 3% inflation, and those don't seem to be very accurate. Have you got any, would you like to add to that, Daryl?
I don't really have
But
much to add.
looking at recent projects, uh, you can find recent projects that were done under like SRF or USDA, or just talk to get bids from a uh, consulting firm. That's the best way to get a good cost for replacement.
Okay, and then the last question we have on the list for right now is from Adabawala, and I hope I got your name right there. What is the best way to convey to the board of the town that monies need not only to be set aside for paying back a capital cost loan, but also yearly maintenance and replacement cost?
Yeah, I think that those costs typically are put into the budget as I've done. The annual costs, the operation and maintenance costs, routine stuff is usually part of the approved budget. Um, so yeah, I don't know.
I have a personal experience with this. Uh, I was in a operator and manager in a town that had not raised rates for Uh, they had raised rates 12 years prior, but not enough. They were afraid to raise rates because they didn't want the community members to have something against them, I guess. But what changed their mind was actually an asset management plan. The thing we're working on today, if you can assess all of your assets and show the board the cost of all the associated things that need to be done to prevent compliance issues. The board are the ones that are on the line when there's compliance issues. Um, if you can show them the true cost and asset management plan, and especially have a third party uh, like us at the Environmental Finance Center or Rural Water or an RCAP person present that as a third party, that is a powerful way to get the board to understand and to allocate those monies. Would you agree with that, Daryl?
Yeah, yeah. Anytime you can get outside uh, confirmation, it's, it's helpful.
All right, we're gonna move right in here as we're getting ready to move to the close today. The last portion we're going to talk about today is condition assessment uh, strategies for collection mains. And when we do condition assessment, obviously we're trying to figure out what the condition of the asset is. But what does that mean? We want to know for each asset, uh, using our inspection technologies, what needs to be done to maintain or improve the performance of the asset. And also, we want to also have information that's going to help us prioritize and plan. So we want to know when it needs to be done and how much it's going to cost. We hope to arrive at that amount of information when we're done with condition assessment. And we're going to look at four general ways uh, here to assess the condition of the collection system. We're going to spend a little bit of extra time on inflow and infiltration. Then we'll look at smoke testing, CCTV, and a couple other technologies here. Now, inflow is the water that comes into the system through rainwater, usually through deliberate connections. And you see at the upper right of your screen, there's a rain gutter downspout that's going into the collection system. And of course, yard drains that are connected to the sanitary sewer. And on the bottom right of your screen is a sump pump. And groundwater that seeps into basements is pumped out as a sump through the sump pump, and it's not supposed to be connected to the sanitary sewer, but it often is. And a lot of that is done innocently, some are not so innocently. You can also have cross connections directly with the stormwater system. Also, another source is just water pouring through into a manhole. You don't have a well-sealed manhole, and rainwater or floodwater can pour in. The other I is infiltration. That is groundwater that's seeping into the collection mains because you have some kind of damage, a crack or an open joint. And you can see here on the bottom right of your screen, you have some water actually flowing in. This is a closed caption TV image uh, of a of a collection main. You can see water pouring in, active infiltration. And so there's lots of different things that can happen. Here we have a diagram here. We have that sump pump that's going to the sanitary sewer. We have a rain gutter that's going into the sanitary sewer. We have a deteriorated sewer pipe that is allowing groundwater in, manhole that has cracks that's allowing groundwater in. And we also have a couple different instances where there's cross connections between the stormwater system and the sanitary sewer. So the challenge is differentiating between inflow and infiltration. And here's an example of there was a manhole with infiltration, and this contractor has grouted the manhole, and they're following up with an epoxy coat to prevent uh, corrosion from occurring. And some other options to rehabilitate a manhole might be using a cured in place pipe liner, which we'll look at tomorrow, I believe, or actually just replacing the manhole. Those are some examples of other options. So inflow and infiltration. The first, there's basically four things we're going to look at here. First of all is knowing the average daily dry weather flow. That's a specific term. And if you're looking at the average daily dry weather flow, it could be for the whole system where you're looking at the headworks, how much water is coming in from the entire system, or it could be the flow coming into a monitoring point. Let's say you're monitoring a manhole that represents a portion of the sewer. The average daily dry weather flow is the amount of wastewater that's actually being delivered in the pipe. That contrasts with the base wastewater flow. The base wastewater flow is the wastewater that's actually coming out of households. And you could determine that um, if you had a way to, for example, meter the drinking water that comes into a house during the winter, for example, when you're not outside watering lawns and so forth. And in on average, it's about 100 gallons per day per person. Now you can determine the infiltration by subtracting the base wastewater flow from the average daily dry weather flow, like this. Let's say, for example, the average daily dry weather flow was 160,000 gallons per day, and the base wastewater flow was 150,000 gallons per day. Your infiltration would be 10,000. 160,000 minus 150,000 gives us 10,000 gallons per day. So that's groundwater infiltration. We also want to know about wet weather flow. To determine inflow, we have to compare the wet weather flow to the dry weather flow. So we would look at the average wet weather flow. In this case, these are just made up examples. These are not taken from an actual system, but the average wet weather flow, let's say it's 180,000 gallons per day, minus the average daily dry weather flow of 160,000 gallons per day. That would give us a difference of 20,000 gallons per day. Now, if you could if you could inspect the system and find sources of inflow and sources of infiltration and repair those, in this case, you'd be saving 30,000 gallons per day of rainwater and groundwater that's being pumped, sent to the treatment plant. So that represents a lot of pumping and electrical use, and it also can upset downstream operations such as treatment. So that's basically the process. And we're going to give you a chance to calculate that. We have a problem here that says the average daily dry weather flow is 259,400 gallons per day, and the base wastewater flow is estimated to be 189,500 gallons per day. And we want to estimate the amount of infiltration. Okay, it looks like we're up to a pretty good amount of of participation here, 75%. I'm going to go ahead and end the poll. I'll give 10 seconds if you want to get an answer in. Okay, I'm going to end the poll here and share the results. And the great majority of everyone said answer C, 69,900. And we can see the solution to that. We simply just take the average dry weather flow and subtract the base wastewater flow, and we get a overall infiltration of 69,900 gallons per day coming into the system from infiltration, which is a significant amount and something that we often see in aging wastewater systems. Uh, Lori, could I ask, is my audio holding up still okay?
You sound just good, working
Okay,
good.
thank you.
Mhm.
Now, when we're going to conduct this kind of analysis, it's good to have a map of your sewer. An as-built map is good. This is an example of a map here. You can see what kinds of information is in a good sanitary sewer map. First of all, the size of the sewer and the direction of flow. For example, here we have, I just circled a 15-inch main, and that 15-inch main in this particular example is a interceptor main. In other words, it's the main uh, trunk sewer that all the other sub-sewers connect, or the sewer sheds connect to. So that's a significant line, and it goes all the way down to the bottom, and it changes to a 18-inch down lower. So that is tracing through. Also, locations of manholes are and the name of the manhole is identified. Those are good points uh, potentially to monitor the flows. Also, there's a structure number where you can actually, it's a good idea to have each manhole labeled so you can identify your sections of main from manhole 1 to manhole 2, for example. Also, there's going to be a scale. It gives you, in this case, there's a 1-inch to 100-foot scale. So if you had 1 inch on the map and it's printed at the appropriate size, you could know that's 100 feet. And we have a couple of locations here where sections of the sewer connect to the interceptor main. Sorry. Where those arrows are pointing are to manholes that represent interconnections between the subsewers and that main line. And so here's a simplified example of that happening. We have sewer shed 1, which serves multiple homes, connects to the interceptor sewer, and sewer shed 2 that connects to the interceptor sewer. And we may want to investigate the degree of inflow and infiltration coming in for sewer shed 1 and sewer shed 2 and be able to compare those and find out if there's overall problems, if we need to investigate one of these sewer sheds at a higher level of priority than the other. So how could we compare the I&I between these two sewer sheds? Well, we'd want to know what each sewer shed is delivering in dry weather and wet weather. And there's a couple ways that we can assess it. We can look at the flow per day per inch mile of pipeline, or we can compare it to per capita estimates. And we're going to show you both of those. So we might set up some kind of flow monitoring at each of these locations at a manhole where these sewer sheds connect to the main interceptor sewer. And so we'd set up some instrumentation at that manhole. And this is an example of some instrumentation. Typically, what is used is ultrasonic equipment to detect the level in the manhole, and ultrasonic equipment that measures the flow velocity in the sewer at that point. And then you can get a flow. There's other data too, like how high in the manhole water is raising. But in general, we have a sensor that points downward, that tells you the level of the flow. And then we have an ultrasonic meter that measures the velocity of flow. And those two things combined are logged and processed. And this type of study can go on for a few weeks, or it can go on for several months, because you want to capture what's going on during dry flows and wet flows, when groundwater levels are high, when groundwater levels are low, and so on. Now, inch diameter mile means that you're taking the diameter of the pipe in inches and multiplying it by the number of miles of that particular pipe in the sewer shed. So I'll give you an example here in a moment. And we take the gallons per day. That's the gallons that are flowing at that manhole that we're investigating over a 24-hour period. And what we're looking at is to compare it to this rule of thumb benchmark here. And that benchmark, it's somewhat arbitrary, but it's a well-used benchmark, and that is 1,500 gallons per day per inch diameter mile. If we're over that, that's considered excessive I&I, and we need to take some kind of additional action to differentiate between inflow and infiltration and some type of corrective action. It might be repairing pipes that have cracks and open joints. It may also be removing interconnection between the storm sewer and the sanitary sewer. And here's our example. We have two sewer sheds, and we're going to compare them. Sewer shed 1, uh, we have 4 miles of 8-inch pipe, 2 miles of 12-inch pipe, and 1 mile of 15-inch pipe, and the average flow is 251,000 gallons per day. And so if we put those numbers in, it would look something like this. There's our 4 miles of 8-inch pipe. We'd represent that as 4 miles times 8 inches. The 2 miles of 12-inch pipe, 2 miles times 12 inches, and the 1 mile of 15-inch pipe, 1 mile times 15-inch gives us 71-inch miles for sewer shed 1. And sewer shed 2, it's the same process, 5 miles of 8-inch, 2 miles of 10-inch, 4 miles of 12-inch, and 3 miles of 15-inch. We get 153-inch miles. So you see, we can compare these two even if they're of different sizes. Then we can do the calculation by taking the daily flow for each one and divide it by the total inch miles. So the first one, for sewer shed 1, we had 251,000 gallons per day of flow. We divide it by that 71-inch miles, and it gives us a figure 3,535 gallons per day per inch diameter mile. Now that is over 1,500, so it's excessive. But let's compare it still to sewer shed 2. Sewer shed 2, 352,000 gallons per day divided by the 153-inch diameter mile gives us 2,300 gallons per day per inch diameter mile. Now, sewer shed 2 is also over 1,500. So both of these have excessive inflow and infiltration, but which one is the priority? The priority is the higher one. The 3,535 gallons per day per inch diameter mile is going to be the sewer shed that we're going to perform additional investigation and probably repairs. We can also compare to the EPA benchmark standard, where they use per capita. And so in this case, you would be taking the average flow and dividing it by the number of people served in that sewer shed. So if in the dry weather flow, anything over 120 gallons per capita per day is considered excessive infiltration. And during wet weather flow, anything over 275 gallons per day of inflow is considered excessive. So in dry weather, you're measuring infiltration, and in wet weather, you're measuring inflow. And so you could use both of those to make a case for needing to repair or inspect. In a particular system in Australia, created this map here. Engineers went through and they did that exact analysis through through looking at each sewer shed within their system, and all the red areas are areas with excessive I&I, and they numbered them and they targeted those for rehabilitation, inspection and rehabilitation, and they were able to reduce their infiltration by 70% um, pretty quickly because they found the highest priority areas and they solved them. I'm going to give you a chance to try this inch diameter mile calculation. And in this case, we have a sewer shed that has a half a mile of 12 inch, 1 mile of 8 inch, 2 miles of 6 inch pipe. And the average flow is 37,990 gallons per day. So you want to calculate the gallons per day per inch mile. And we can give a few minutes for this. I'm not sure if you would like to set a timer, Lori, but we want to give people at least 3 minutes to do this one.
Okay, sure. I'll start a timer.
We have about 30 seconds left here. Okay, thank you, Lori. All right, we're gonna go ahead and end the poll. And if you were still trying to do this, I apologize for stopping it sooner. But it's the first time you've ever done this problem. But the great majority of everyone said 1,461 gallons per day per inch diameter mile. And we're going to look at the solution for that, and that is the correct answer. We set up our inch diameter mile formula like this. We had a half a mile times 12 inches. 1 mile times 8 inch, and 2 miles times 6 inch. That gave us 26-inch diameter miles. And now we're going to take the flow and divide it by the inch diameter mile. 37,990 divided by 26 gives us 1,461.15 gallons per day per inch diameter mile. And that's below 1,500. So we're below what would be considered excessive infiltration. We're going to go on to a different way of inspecting, which is smoke testing. Uh, the inflow and infiltration studies they require some equipment and some time. Smoke testing uses relatively simple equipment, and it gives you immediate data. It's usually something that operators can do when they have uh, a day that they can spend on doing this. You don't necessarily have to have a specialist come in like you might have to do with inflow and infiltration studies. And you could see an operator in this image on the slide. The smoke testing machine fits right on top of the manhole, and some liquid smoke is being fed in, and that is blowing smoke down into the collection system. And you can see some smoke coming up through a crack, and you can see that that the smoke is visible, and so you can know that there is some kind of defect in the collection main. Here's a couple images going from left to right. On the left, you can see a couple operators. They're placing a smoke tester on top of a manhole, and they're running it. The second picture from the left, you see smoke coming out of a house roof vent. That's normal. The sewer vent is supposed to allow smoke to come out through it. But picture number 3 has some smoke coming out of a lawn drain. That's not supposed to be coming out there. So you notice the operator is documenting that smoke. You can categorize that smoke as light, moderate, or heavy. I would I would say that is probably somewhere between light and moderate, but the more smoke, the bigger the problem. And on the far right, you see some smoke coming out of the ground. It's interestingly near some kind of a utility pole. So when that utility pole was placed in service, did it damage the manhole down below, the sewer main down below, causing some smoke? Or is there some type of clean out there? We don't know. That operators are investigating it. To set up for a smoke test, you'll plug off a portion of the sewer. You'll use a sewer plug. These are inflatable plugs that can be placed so you can isolate a section of the sewer, usually manhole to manhole, so that when you smoke, you're looking at all the homes and the sewer line between those two manholes. And you can see that there's some smoke coming up out of a crack in that right-hand picture there. So you put the sewer plugs in. They're inserted in, and then they're inflated with a air compressor. And you can see an example of a sewer plug, what it might look like. And you have a way to release the air up on top so you can pull it back out. And you see where number 2 is, the smoker's placed on the manhole, and it has liquid smoke that is purchased that feeds into it. And then you view and record the results and take photographs. Here's some examples of what you might see when you run a smoke test. First of all, would be smoke coming out of roof vents and out of the tops of manholes. That's normal. That's nothing wrong with that. You'll likely also see some smoke coming from some rain gutters. That's a source of inflow. And if you see smoke from lawn areas, it could mean some kind of interconnection or maybe just an uncapped cleanout. It could also be a break in the lateral, the lateral that's serving that home. You might also see smoke coming from uh, points along the main where there's damage, or the sides of the casing of manhole where there's actual cracks or damage and smoke is coming out, or smoke coming from a storm sewer. which would tell you that there's an interconnection between the storm sewer and the sanitary sewer. So those are useful. If you combine smoke testing with these other methods, it'll give you a good overall um, way to assess the condition of your collection mains. CCTV inspection, as you can see, the little robot that's moving down the sewer line. You're actually sending a TV down the main, and you're looking for things like cracks and defects, infiltration. And here's some examples here. You can see on the upper uh, left of your screen, you can see an active infiltration coming on. It looks like a poorly grouted or deteriorated joint between pipes, and it looks like maybe a crack there. There's been a crack uh, closer to us. On the lower left, you can see the operator is able to view in real time, but these are also recorded, so you can view them later. You can actually view on a screen what's going on down underneath as the machine passes through. And on this particular image here, you can see that the person that's operating the camera and robot is viewing on a screen, is controlling the device, and in this case, a device that's a self-propelled mud monster. That's a brand name, I believe. It You notice it has wheels, kind of like a little four-wheeler, and a camera. That camera can be moved different directions. It can go forward or reverse, so you can take a second look at defects, and then those defects are uh, coded, and the exact distance into the setup from the manhole, and the type of defect and how large it is, details about the defect. And you can see on the right of your screen that the truck is backed up right to a manhole, and that camera is launched. And usually this will be manhole to manhole. Here's some examples of how the results might be coded. You see there's some codes here. There's RJ, and OJL. What do those mean? This one here, RJ at 3.3 meters into the main. It was roots at the joint. And another roots at the joint. And an open large joint. The joint is actually open, which would allow infiltration to come in. And you notice it tells how far into the main, the position. And also the codes will include, the information will include how big like a crack is. And here's sorry, it's not very clear, but here's a page of the different types of codes. Like for example, C for crack. It could be longitudinal, circumferential, multiple cracks or spiral. There's a fracture where the crack it's more than a crack, it's actually separated. And so there's different types of codes that are used to describe the condition. And these are NASCO codes, and that stands for the National Association of Sewer Service Companies. And they have the PACP, which is their pipe assessment certification program. You can become certified in that, and it allows you to be able to um, conduct condition assessment using the CCTV data. We'll look at a couple of the technologies as well. And we have a picture of a sewer line rapid assessment tool here, which we'll look at. But one is this electrical scanning technology. They have a truck that backs up, and they send a, uh, a probe through, and it sends out a low voltage current through non-metal pipes. And so it's measuring the electricity that goes to the ground. And so it passes through, and so you can determine the location where we start getting electricity going through the to ground, and it tells us that there's some type of defect. A larger crack, more electricity will go to ground than a very small pinhole. But you can get an idea uh, fairly economically if there are defects in a pipe. Now, the sewer line rapid assessment tool, it uses sound waves, and it's basically about detecting blockages. Now, blockages could be something like the fatberg, like Daryl talked about earlier, or it could be where a main has collapsed. And the good thing about this is the operators a couple operators can assess quite a quite a few linear feet in a day. They estimate 10 to 20,000 feet per day can be assessed. And so it just results in a score from 0 to 10, 0 meaning the pipe is completely open, 10 meaning it's completely blocked. And here's a video that was provided to us. See the receiver. There's a receiver at one of the manholes and a transmitter at the other manhole. He's going to get a reading in a moment here. You notice he got a reading of 8. And this video was provided to us by an operator, operations person just like us. And if you have anything if you have videos and examples or photos you'd like to share with us that we could use in a training, that would be great. This was provided to us by Ahmad Giwa, who's a wastewater collections and GIS supervisor from Viola Water. But a score of 0, it's totally open. There's no obstruction. 1 to 6, I'm sorry, I said that wrong. A score of 0, I said, I meant to say it's totally blocked. 0 means it's fully blocked. A 1 to 6, it's varying degrees of blockage. And a score between 7 and 10 indicate that the pipe is flowing freely. So this example is an 8, so the pipe is operating fine. We can also use GIS technology to compare where our lines are compared to other sensitive features, like a sensitive waterway. Do we have a pipe flowing over a protected river? Or do we have a pipe that's flowing in right into the downtown area next to schools and hospitals and so forth? Those types of overlays can help us to determine pipes that have greater priority for inspection and rehabilitation. Following condition assessment, you'd want to analyze the results of the investigation and also do that comparison with the GIS of considering the extent of outage. What would happen if this main were to have a sanitary sewer overflow or a break or some kind of a failure? How would it affect transportation, population health, and environmental aspects such as rivers, lakes, and streams? And determine the type of repair that's needed and make a plan with costs and dates. And we're going to do our final poll of the day here. And the question says, smoke testing a collection main results in heavy smoke coming from a nearby storm drain. What could this mean? Somehow I lost the ability to see the poll, Lori. So when you see it get up to enough people, maybe you could let us know what the results are.
Okay, will do. Okay, sharing the results now. We had 97% of the people who responded, which is 73 people, said answer B.
Thank you very much. Excellent job, everyone. And this is a common problem. And we posed some essential questions at the beginning of the today's training, and we want to see how we did. And so the first thing we asked is what types of things can happen to assets that leads to the need for replacement, repair, or rehab? And what did we say today? We said that assets can deteriorate over time due to corrosion and wear, or a subcomponent can fail due to root cause factors. So environment is important. What are ways we can analyze the current state of our assets? We can use condition assessment to provide the information we need to rate the condition of assets. And also we can create an asset inventory so we can have a framework to record asset information. And how can we predict and prevent asset failures? Well, one of the ways we can use failure mode effect analysis to help us predict causes of failures and inspection technologies to help us detect a failure that's about to happen before it actually fully occurs. Today, we looked at a lot of topics. We looked at the components of asset management, and we looked at some condition assessment strategies. But the three main takeaways are under condition assessment, the asset performance data helps us to plan cost-effective maintenance, repair, and replacement actions. And we talked about criticality. That's used to create priorities. We identify asset priorities, and then we can implement some kind of strategy to minimize the risk or repair those assets. And finally, the asset inventory. It provides us a framework to collect asset data and helps us to make decisions in the future. And tomorrow we're going to continue on with this. We're going to get into some more condition assessment, talking about lift stations, and we're going to talk about some rehab and replacement options for sanitary sewer collection systems. And also we'll talk about some maintenance strategies and some financial planning tomorrow. And so I want to close right there and open up for questions.
Okay, as of right now, I don't have any questions on the list, but I invite you to throw some our way if you have any additional questions or thoughts. And while we're looking to see if anybody has any extra questions, I did put in the chat a reminder to please use the same Zoom login that you used today to log in tomorrow. Just same one. It's straightforward and easy. And yes, it is the same time, same start time, same end time, just tomorrow for day 2. Okay, a question for you, Greg. This is from Sarah. How accurate is the sewer line rapid tool assessment in identifying blockages?
That's a good question, Sarah. It's uh, it's it's more general. Um, like for example, if you had an 8, you notice that the 7 through 10 was considered to be that the sewer line is operating fine. So it's more general. It's not as accurate and precise as something like CCTV. Um, it's more of a general indication. So probably how you would use it, anything below 6, you send your crews out to to maybe do some cleaning or inspection. And it's always possible that um, the lower numbers are, of course, are going to be more serious. And so something that's a 0 or 1, that's going to be your priority, but it it's not a precise measurement. It just gives you an idea what you should go and inspect.
Okay, Greg, I have two of the same questions. This is from Ryan and from Lorraine, wanting more information on how to do calculations for I overflow.
That's a good question. And let me do a little bit of research, and a I'll bring you what I found tomorrow. That's important, I know, for compliance. And so if you give me till tomorrow, I'll have a better answer for you tomorrow.
Oh, I'm sorry. I have a clarification. Lorraine was not asking for more of that. She was stating she learned about that today.
Oh, okay.
Sorry about that, Lorraine. I misunderstood.
Oh, I see. Yeah, but still, the amount of flow from an actual sanitary sewer overflow, that would be something good. That's what I was thinking of, and so that might be something uh, that would be something good to know as well. So I'll research that still.
Okay, so we at this moment don't have anything else on the Q&A list. So if you do need to exit the meeting, you are welcome to leave for today. Thank you for your time and your questions, and we will see you tomorrow, same time, same link. And what I like to do is just kind of hang out here and keep the session open just for a few more minutes in case anybody has any lingering questions or thoughts, and that I can put those on the Q&A list for tomorrow. So that's what I'll do, and I will give a warning before I close the Zoom session down.
I see your question, Sarah. How do you factor the information collected, the CCTV, smoke inspections, into the criticality for score for the asset? Um, I don't have a short answer for that. Um, However, we have been working with some engineering firms that are trying to do just that as part of a there's a term called sanitary sewer evaluation survey that's required um, by funding agencies uh, to put money toward a rehabilitation project. And in reality, the smoke testing was really mostly in the most recent project we're using. It was mostly used to establish the need for CCTV. So the smoke testing told them where they needed to look and what they needed to look for. For example, smoke coming out of the ground uh, told them that we need to look for pipe defects in this particular area. And smoke coming out of a storm sewer told them, hey, we need to look for interconnections uh, with the storm sewer, or maybe it's a bunch of connections to people's sump pumps in the roof veins. So if you might not be able to do smoke inspections and CTV for the whole entire system all at once, you might just have smoke testing data, and that would be the basis of your condition assessment. Um, but if you're going to use CCTV, the smoke inspections would tell you where to look. It's more expensive to do CCTV, and so you don't want to waste time and money going over sections that you know are good, if you know what I mean. You would look at that worst 10%, so you're using your time and money effectively. I hope that answers the question okay.
Yeah, at this point, Greg, we don't have any additional questions. Um, So I'm going to just kind of leave the session open for 5 minutes here. And if we get anything else, I'll let you know. Otherwise, I'll give a warning right before I close the Zoom session down so nobody is surprised. But thank you for your time today, Greg, and to you, Daryl. Um, and we'll be back at it again tomorrow.
Yeah, I see Sarah's question here. Uh, are the 1 to 5 rating for POF and COF based off Michigan requirements, or is that the industry standard? It's actually kind of based off the US EPA practices. They US EPA has actually has asset management training material, and I think it might be one of the links on the references document. If it's not, I can find it for you. But uh, you don't have to use 1 through 5. You can use any range of rating that you want, but 1 through 5 happens to work, and you're not stuck with just a 1 or a 2 or a 3. I mean, if you wanted to get more precise, you can have a 1.5 rating, for example. But normally that's not really necessary. Um, what you're looking for is that, that 10 or 20% of the assets that are the highest priority to fix first. But I've seen asset management ratings where they used a 1 through 8 scale or a 1 through 10 scale. So 1 through 5 is just one example, and it's used by the US EPA. But we're doing our best here, Sarah. Thank you for the great questions.